is Ibrahim Aburawi, and I'm going to show you how to run cyclic analysis in Abaqus using the SAC loading protocol for a steel solid elements. The type of the beams and the columns that has been used in this analysis are as following. This is for the beam and this is for the column. First, I'm going to show you the interface of the Abaqus that I'm currently using. As you may notice, I'm using the Abaqus CAE Student Edition, which means that I am limited to 1,000 nodes in this analysis. So this edition, this Abaqus edition can't be used for running a good or accurate to obtain an accurate results. When creating the parts, so start off with the models. When you're creating the models, there are two ways. The first way is by just creating the parts and then assemble them in Abaqus itself, or using an alternative drawing tools, SolidWorks, AutoCAD, or Revit, or many others, and then export the files as to Abaqus. In here, we are going to use AutoCAD to draw our parts. First, you have to decide whether you are carrying out a solid elements. You're gonna analyze the solid elements, or you're gonna analyze shell elements. And here we are using a solid element, so we are gonna use this one. So to create our HE, as we said earlier, HE 180. We just need to carry on. So in here, this is the dimensions of the beam. As we can see, 180 mil is the width of the flange, and 152 is the length of the web, 9.5 is the thickness of the flange, and 6 mil is the thickness of the web. So we need, as we have said earlier, this beam is 1.2 meter long. So in order to get the length of the beam, we have first to make sure that this is as a boundary. It's moving as a boundary, is not just like a lines. And then just we type extrude. So we should extrude this, and we said in order to have a better. So this is our solid beam. So to change the view, we can make it realistic. So this is our solid beam. Now it's been created. So this is one of the most important steps. So now, in order for Abaqus to recognize the drawings, we have to save the file as SAT type. And how to do so is by the following steps. We just choose the element, type export, and then we have to bear in mind that the file where we should save it. So I am just like saving it in here in Abaqus, And here you can see two solid beam and column because I have initially produced them before I start the video. So to speed up the video link. So in here we can see we can name it solid beam 1 and make sure this is ACIS SAT type, and then click save. Then you have to reselect the entity and click enter and then cancel. So now this one is being saved to Abaqus the same way you do for the column, but as we said, like for the time to make it this video as shorter as possible, I have created this and I'm just like going to move to Abaqus now. So to start off with Abaqus, you have first to define the parts. You have to bring the parts in. By doing so is click in parts and then import. This is the one we have created, solid beam 1, but for them to make sure that solid beam I have created earlier and the columns, I am sure about the dimensions, the right dimensions, using the right dimensions in those two. So I'm gonna just import solid beam. And then you see in here, it's SAT, and this can be read. So these are the types of the files can be read in Abaqus. And then click solid beam. And here it shows to you like, do you want to keep it the same name, everything, just accept defaults. And here you go, you've got the beam. Now you've got the solid beam. So now we have to do the same thing for the column. Click on the column and click OK. And then accept the defaults. So we have now imported the files, imported the AutoCAD files. That's a great job. Now, before moving any step forward, we have to save the file. So this is also one of the important steps you have to remember. I'm going to just name it demo. You have to remember where you have saved the file. So I have saved it under Abaqus. The next step is also important because you have to set the work directory. Otherwise, if you are running it in university computers where you have like a limited memory drive, so you have to set the work directory if you have a large job sizes, as the case for cyclic analysis. Usually it's up to 40 or 50 gigabyte. So it's like quite large, big memory is needed. So you have to set the work directory. It's not automatically set on the E drive. I have to go back and search for where I have saved my documents. So I have saved it under Abaqus, and then I just click on the Abaqus and click OK. And change now University Docs Abaqus. This is where it's saved now. And then click OK. Now we should identify the materials. Some people prefer to use the module tree in here, the models tree, but I personally prefer this drop-in menu. It's much easier and much faster. So like we have to carry out all these steps, and like for the optimization, we're not gonna look at it, and the optimization and the sketch, we are not in here, we are not in this drop-in menu, we're not gonna look at it, and we're gonna check all these menu. So for the property, in order to create, we need to create a material and then create a section and assign. The third and the last step is assigning that section to the elements that we have. So creating materials, we're going to name it as steel. We can define the density of the material. And then we can define the elastic and plastic. So it's E3 and the Poisson ratio of 0.3. We can also define the plasticity. If we have a results from a component test, or we have results, we have found the results from any source online, so we can just use it, or we can ignore it. For this time we're gonna just ignore it. We're gonna just use the elastic and we're just defining the density of the materials. And then we should create the section. We call it as section 1, and here I'm talking about the solid and shell elements that I talked about earlier. So if you are analyzing a shell element, you should have used the other, you should have opened the other type in AutoCAD. So the section should be homogeneous, section 1, continuing, and then we should choose the material that we just created. Okay. Now third step is assigning that section to the material, to the elements that we have created. So we have to select the elements, click done, make sure that the section is the section 1, solid homogeneous, and the material is steel. It's great. It turns to green. That's perfect. Good job. And move on. So we have to do the same thing for the solid beam. Assign the section. Make sure everything is in. And click OK. So now we have done the property. So we have to go to the assembly now. In order to make the assembly, we have to create an instance, and these instances can be dependent on the mesh or independent on the mesh. I personally prefer working independent. That makes the life easier a bit. So now we have to make the column, bring the column and the beam in, and make sure they are auto offsets from their instance. So they are a bit away from each other. And here for this, so in here, in order to assemble those two instances that we have brought, we have first to rotate the column. So in here, rotate instance, click the column and click done. Choose 2 points and 90 degree, press enter. And then click OK. So the column has moved. So we need to move the column to the origin point. To do so, from here, translate instance, click column, OK. Choose the point. And then choose here. So the column has moved to the origin. The beam. For my particular beam, I'm gonna use first a reference point. in order to attach the beam to the column. And to create a datum point, so we're going to create a datum point. So click on the datum points. So we have to define the X, Y, and Z. Mine is going 60 on the X, but as we can see, the 60 is off the column, so it's going to be negative 60. And on Y direction, it's 813, and Z direction is 0 because we don't need any. So we need just on the beam, so on the face of. Click enter. We'll see a datum point is created here. So to easily bring the beam, we can just use the translate instance and click done. Choose the point, reference point, and then choose and click OK. So in here, we've got the beam and the column are in place now. So everything looks great. We can do some partitions because this partition will help us for the meshing later on. We don't have any other parts, but if we do so partition is really needed. So we can have partition edge or face or cell, different types of partitions. In this case, we are gonna just produce the face partition. But to do the face partition, we have first to create datum plane. Datum plane in XY. It's gonna be 1000. As you can see in here, 1000 went off because on the X, so I was a bit mistaken. So I should just right click, delete, edit, and a negative 1000. Apply. Can make another partition. So in YZ, see this one is in the middle, exactly. This type of partition is made mainly because later on the loading, we'll see we'll assign the load to this point in here, to the intersection point. Sometimes it's hard to do the reference points. Abaqus doesn't recognize the reference points, so it's easier to do it through the partition. So to create the partition, click create and choose phase. Use datum plane. So you choose, it says individually, we're just going to use by phase angle, So we're going to use this one, then okay, click this, the datum plane, create partition. So we have to do another one. If you want to multi-select, you should press Shift, click, done, partition, create partitions. Sometimes it gets spoiled and gets so much if you have increased the number of datums. So to hide the datums, you click View and Assembly Display options. Datum, show datum planes. Just untick that and apply. It's easier to see now the instance and to see where we should apply the load later on. So now the assembly and the module, we have finished it. To create the step for the cyclic analysis, the step is very important. And here we are gonna just use a general static. Gonna call it a cyclic step. Continuing. And here we have to pay an extra care about those 3 boxes. And here you have to make it as big increments as possible. So to make sure that the analysis is completed. So I'm just going to make it 100,000 increments. And this one, I'll come back to it later on when I define the amplitude. So I'm just like going to accept this one for the time being. And that's great. After finishing the step, we should come back to the model database. Drop in here. So we choose the field output. So what output would we like to see when we run the analysis? I would like to see the stresses, strains, displacements, forces, reactions. Would I like to see the contact? No. Okay. Would I like to see the energy, failure fracture, and so on and so forth? For the time, I'll just accept the defaults. And how many increments I would like? Every increments, every 1, every 2, do it every 5. It's how you'd like to see to represent your results. Now we go to the interactions. Although we have connected the beam to column in here, but Abaqus still treats them as 2 independent parts. After choosing the field outputs, now we can go through the interactions. As we mentioned, interaction needs to be defined in Abaqus, so to make a connections between the 2 parts created in here. And here just a tie constraints will be used. To make the life easier, we should create the surface and tie it to that. So in here we are gonna go back to assembly and surface. Create a surface, name it as solid. Beam. And now we need to choose this part of the solid. So we need to hide the column. To hide the column is click. We need to change this one to instance. Done. Escape. Now we have to choose this part here. So we choose. Now check this. The solid has been assigned to this. So this section has been assigned to this type. To bring back the column, we literally click and replace all. So now we've got. So we need to make another, say, another surface. Call it column, and we should choose the surface. Click OK. So if we go back to the interaction, just close this assembly. If we go back to the interaction, we click tie constraints, and then here easily we can do just click the surface and choose surfaces. To choose the master surface and the slave surface. The master surface should be the deformable element, and here in this case the column is fixed from top and bottom, so the beam is the deformable element. So we should use, to see it on the plan, as highlight on element. So this one should be the master surface. Click continue, and then ask you for the slave surface. Choose the beam. So to check master surface is a solid beam, and slave surface is the column. Analysis default, and then accept. So now we have created the interaction between. For the load, now we go to the load module. First we have to create the load that we have set. So it's gonna be on the cyclic step that we have created earlier here, and it's gonna be before creating the load, we should first create the amplitude. So to create the amplitude is click a tabular amplitude, and this is SAC loading protocol that we have mentioned at the beginning of this video, and click continue. So we need to place the time and the amplitude. So in here I have extracted this cyclic loading protocol from FEMA 350 document explaining this cyclic loading protocol. For our part, I have created my own amplitude, so we are gonna copy this for the solid and the column, copy it and just paste it in here. So now we have the full cyclic loading for the solid. As I said earlier, this one, we have to remember this first one and this last one. So the first one, 0.0078, and go back to the steps, incrementation, and 0.00788125, and the last one is 1, and the minimum that would go is 1 to the negative to the power 1 times 10 to the negative 5. and then click OK. So the amplitude has been defined, and now we are going back to the load, and as we said, we are going to define the load as a load displacement. So the load displacement techniques is used on the literature, on many research. So we applied a 1 millimeter displacement at this point, and we call it as load. This is a uniform. U1 is in X direction, U2 is in Y direction, U3 is in Z direction, and this is the rotational for each axis. So in here, we need our beam to go up and down to replicate this cyclic protocol. Thus, we need U2 to make it just 1, and the amplitude, we should change it to the amplitude that we have created, which is SAC loading protocol, and click OK. Also, we have to make the boundary condition for the column, and this is usually assigned through the initial step. So we should choose the top and bottom parts of the column. As I said, for multiple selections, you should use Shift and click. So now we have chosen the bottom one, top and bottom, and call it boundary condition. I'm gonna assume it's fixed, so it's in custody. You can assume it's pinned or fixed on the x-axis, y-axis, no rotation. So I'm assuming in custody for this tutorial. And that's it for the loading. So we have defined the loading, and we have defined the boundary condition on the column. So the last step is we go to the mesh. The mesh, there are like few rules you should bear in mind when you mesh the elements. So first thing is the elements type. The element types, which element types you are using. Are you using standard, linear, explicit, linear, or quadratic? Or to speed up the analysis, we are just going to use the standard linear hex with the reduced integration element type. So this is the C3D8R type. You can use a wedge or tet, but these are going to take a bit of longer time to run. As we can see, this is the cyclic behavior. We know that the values and the stresses, strains distributions are not accurate or not precise due to the size of the element, but the aim of this video is just to show you how to run a cyclic analysis. I hope you have enjoyed my video, and thank you for watching.